The next talk is titled Identifying Predictive Causal Factors from News Streams, to be presented by the first author, Anant.
Hi, everyone. So this work was done with collaborators at Indiana University, my advisor at NYU, and collaborators at World Bank. There are a few terms that might seem misplaced in terms of like, why are we tying prediction and causation? They're not to be mingled around. So hold on your questions till the end of the presentation, and yeah, there might still be a few questions at the end. So the motivation for this work is illustrated in this example. So if you look at this graph, it's how a shock in an economic network propagates throughout the world. So for example, in this particular image, it's how an effect of a low demand in the US actually impacts other countries' exports across the world. Now, if you look at this image, it's not very clear if you can come up with like very trivial examples of like the proximity. Like you need much harder causal factors that would be indicative of how some of these export drops that you would notice in countries that are probably far away from the US, and like how trade is done between these countries. So these set of economic factors or causal factors that you would expect to understand might be prevalent in the news. So the motivation is actually, can we predict or explain certain real-world social and spatiotemporal phenomena, such as fluctuations in economic indicators? And there are multiple other factors of different types of indicators that you might see in terms of like as macro as like the GDP prediction, or like how poverty has spread over in a particular region, and so on and so forth. Again, the claim and the disclaimer is we are not interested in actually explaining to the true notion of and come up with a causal model, because that is left to the domain experts to validate and hypothesize. But what we can actually do is, given that there are a few causal hypotheses in a particular domain, can we actually use that to leverage to build better predictive models? So if you look at certain news headlines in India during elections, they talk about onion prices becoming very volatile. So this is a kind of a factor that we occasionally observe in the news that might be indicative of an underlying phenomena. So in fact, this work is actually building on top of prior work from the same group, which had this was in KDD 2016. So they were able to condense the kind of predictive factors of onion prices in India to 6 main categories of features. So one was like political events, government policies, natural disasters, even festivals in India have a certain effect on how onion prices fluctuate, and something that was probably non-intuitive to people were like strikes and different kinds of fuel and transportation costs are actually predictive of how onion prices on the left fluctuate in India. So these kind of socio-economic indicators are captured in the news stream, and we want to effectively build better predictive models using some of these factors that we want to extract from the news stream. So that remains the motivation of the work. To identify what we mean by predictive causal versus true causal is like, in a standard causal inference setting, you have, let's say, variables, random variables, x, y, and z. You tend to normally observe only, let's say, z and y, but where x is the unobserved confounding factor. Now, true causal inference actually expects you to identify like both the direct and the indirect effects of even the unobserved confounding factor. We are not in that realm, as I stated prior. Like, we are trying to understand, given a causal hypothesis and what is observed in the news, can we identify those links? And in the news, more often than not, the factors that we care about are actually mentioned in the news stream itself. So this is an example of kind of a semi or a subset of a graph that you can construct using news in India. So for example, this was an indicator of a news event that announced the slum rehabilitation in India. The arrow marks that you see are temporal in nature, so they go from what happened first and then to a corresponding event that happened after a certain number of days. So after 2 days of slum rehabilitation, there was a news of like a committee being kind of coordinated and formed. And probably 19 days later, you saw in the same location, there was news about a certain type of relief being provided. So clearly, these kind of simple subclasses or subgraphs that you can construct of certain very localized and temporal socioeconomic phenomena. The goal of this work is, given an input of a stream of such factors, we have like the time series of the number of times a particular word occurs in the news stream. It may be words, it may be bigrams, it may be any kind of a conceptually valid notion that you see in the news. Given that time series, we want to output a sparse graph with links between the terms or the nodes of the network, where the nodes are actually linked between using Granger causal links. So Granger causality tests, for people not familiar with the literature, is trying to predict future events using current or past events of other nodes. So in effect, the graph that we have in mind would probably look like this. So given a bunch of factors that are relevant in a particular phenomena, you would want to learn some of these links between them. And the assumptions here are we cannot extract all kinds of causal links or predictive causal links. We assume that the cause is observed in the news prior to the effect. So it's kind of like it was reported in the news prior to the effect. And also that the cause has certain kind of predictive information that will lead to better predictions of future events of the effect. So these are the two assumptions that we are working with here. So the idea is to learn a very sparse graph that makes a lot of sense. So if you had like a fully connected network where everything impacts everything, we are not really learning or understanding anything about the corresponding phenomena. So if you focus on a very small part of this graph, you might like look at links which may or may not make sense. So we kind of introduce certain two types of sparsity constraints on the graph that we construct. So firstly, if you notice the two links between terrorism and departments vanished when we added a constraint of sparsity of the factors that we want to capture. So this kind of eliminates certain low coefficients which have low predictive power of the final effect, which is like the word cabinet appearing in the news stream. We also added a topical similarity, which is basically the Jacquard's similarity of the topics between two nodes of when we ran an LDA topic model on the graph. So this kind of captures both the sparsity of coefficients that we want to that we know to be true in the real spatial temporal phenomena, and also kind of captures very similar or topical factors that are relevant to that particular topic. The other thing is, once we have this, let's say, universe of factors that we want to capture, it's not very easy to do very fine-grained prediction, because the set of factors that we want to predict might not be true all the time. So for example, in this particular use case, the effect of predicting the Apple stock using a factor called podcast, which may or may not have semantic meaning to people based on their familiarity with the Apple Music ecosystem and so on and so forth, that kind of varies between over time. Similarly, the word unfollowers, how impactful that is to the prediction of the Google stock might also vary. So the graphs we have predicted here, we have plotted here, are actually the coefficients of the linear regression model that we learn for our model. So clearly, there is a notion of, given a set of factors, we want to choose the best subset of a factor for a given time window. And this we try to use using prior methods of honest estimation. So what that essentially means is that we want to gather a universe of factors that predict well over a longer term, as well as predicts when you fine-tune them over shorter time periods. So this is basically, we try to look at like non-overlapping time periods and try to capture a set of factors which predict well over, first in the green portion of the time series, and then we train multiple smaller models for each of the smaller time windows that we see. And if the error in both of these time windows that we have seen is below a particular threshold, we would want to choose that factor. So not only that, we also want to account for certain spikes by trying to fit an ARIMA model on the residuals between the prices that we see. So it's almost like you're doing two orders of prediction models. How this differs from general news-based prediction of the stock market is, I mean, if you go through the literature, I'll not go through the whole list of papers here, but they try to focus on very stock-specific or financial industry-specific articles. And that's where we want to deviate. And the experimental setup we used for this particular paper is given an input of like the Google News for 3 years and like New York Times data for like more than 10 years. Can we actually predict the closing stock prices of 10 stocks over a period of a year? And we will use the same kind of a predictive causal graph that we used to construct it, and also embed the stock price as one of the nodes in the graph. So we want to capture non-financial sources and how probably that might impact the news. So this table is in comparison with a baseline model, which was presented by Kang et al. In EMNLP 2017. So they use like a very small subset of cause-effect pairs that were extracted from the financial literature and try to model that. Now, our model, which is under PCG uni, bi, and both, which is basically unigrams, bigrams, and if you account for both of them, it gives you significant power in terms of by lowering the prediction error. The error here is basically windowed errors over a period of a year for a month, right? So not only that, we can actually visualize the factors that will come up for each of these stocks. For example, the word music, which was very relevant to how the stock of Apple prices moved around, and which can be kind of illustrated in this news article where they said iTunes had to be shut down on Mac because no one was buying music anymore, everyone streams. So music is a very relevant term to predict the stock prices of Apple, right? So you do kind of like validate some of the causal hypotheses that people have using time series data extracted from a news text. This table is giving us that if you went back to the orange smaller time windows to capture the sensitivity of the news factors, if we expand that time window over a period of time, it actually increases the predictive power by quite a bit. And definitely spike correction improves the RMSE percentages over a period of time. So one additional external kind of confirmation of our framework we did over a different news data set, which is the Times of India data set of almost 10 years. And we actually manually annotated certain cause-effect pairs that we could find in the news and try to see and try to visualize how those cause-effect pairs were in the final predictive causal graph that we constructed. So here you can see between pairs you have very relevant terms that come up. For example, election and strike, there are like 3 different paths to the same set of words, and each of those 3 paths that you see in the network actually are from different regions of India. So it's possible to capture like very different types of phenomena from different types of regions and have different time lags between how each of those terms interact. Now, with respect to future work, we are trying to extend this for more socially aware kind of applications, which is trying to predict famine in regions where there is very less data for multiple reasons. So this is mostly focusing on fragile states. And also try to augment certain cause-effect pairs from authoritative text into some of these temporal analysis regimes. That brings in a very kind of theoretically challenging question as to how do you learn like augmented models of both using both temporal correlation as well as known causal models. So that is something that we are still working on. To conclude, we have proposed a framework to do extracting predictive causal factors, which might be latent in the news, which have both long-term predictivity and short-term sensitivity. And it captures both temporal and topical relations. In terms of application, we outperform prediction over an approach which used known cause-effect pairs, and it can also be used to validate causal hypothesis. I'll stop here and then take questions. Thanks.
The speaker. Questions? No? Question, Ken?
So if anything like this actually worked, wouldn't it be arbitraged out of the system sort of immediately?
Yeah, I think that's one of the limitations of the approach that we are trying to tackle, which is we do not have a system to incorporate new and novel terms that come up in the news text early on. So there is still a period of uncertainty where we cannot incorporate that new element. Let's say a term started to pop up in the news, term X, and we have no predictive power using that term X, but maybe people can understand better of that term X and then can try to incorporate. So there's still a time lag between the inefficiencies of the market to capture, so to say.
Other questions? So one from me. So what would it take to move from predictive causality to true causality, or is that just not a sensible question to ask, and why?
I think I would make a lot of people unhappy if I did claim true causality because of a lot of assumptions that we are not willing to scale and probably are not aware of. One example could be like there could be certain effects which are observable in news which might improve prediction but have nothing to do with causation, right? So it's probably a better, in terms of especially the famine prediction work that we have in the future, it's better to incorporate known causal models that people have and try to augment that with something better or like signals to those causal models as opposed to trying to invent the wheel over what might be causing certain things. Because yeah, there might be two models be equally predictive, but one is completely useless, right? Yeah.
Fair enough. Okay.
So the arbitrage concern I had is a little different. It's that if you had a method to predict anything, and anybody else knew what your method is, then they would do the same thing and just reduce, eliminate all the advantage.
Sure.
So the only way to make this work is to have a method that works that nobody else knows about.
I think that's what most hedge funds would hope that they're doing, is hoping
Right. So
that.
I'm saying if you publish it, then it's not going to work.
I mean, the motivation of this work was not to build like better policies for like trading stock, but just to understand certain phenomena.
Right. But I'm saying those phenomena would go away if you actually did manage to understand anything. Sort of like, quantum mechanics. Once you measure it, it's gone.
Yeah, I think that's true for all causal models. So the moment you know the underlying causal mechanism, people try to take advantage of that, and that causal model no longer remains the valid one. So yeah. Thanks.
Okay, let's thank our speaker.